Hello, Mr. Eric, Mr. Ryan, are you right? Okay. So let's look at the graph. Okay, we talk about the graph. Graph is data structure, right? With the vertex and edges, right? Yeah, vertex and edges. Graph is a collection of vertex and edges. It's a data structure, and we talk about weighted graphs, unweighted graph, direction graphs, undirected graph. Okay, so today we look at these unweighted graph. So we have a node from 0 to n minus 1, right? N minus 1. So for example, like 0, we have 0, 1, to a graph, right? This is undirected, unweighted graph. Like that, okay? We have a graph, right? These are the vertex, and these are the edges. And the number of the edges connected to a vertex, which we call it degree. This can be classified into two, in degree or out degree. Degree is the number of edges connected to a vertex. Okay, so given this graph, if I'm saying that the node 2 and 5, these are the nodes which we are forbidden to go there. Alright? So 2 and 5. Right? 2 and 5 which are forbidden to go there. So can you tell me the number of nodes that if we travel from node 0, how many nodes we can go to? Yeah, 1. Okay, so yeah, this is simple. Okay, yeah. So okay, this is the question. So we're given a undirected, unweighted graph, and we also given a list of the forbidden nodes, and we want to count how many nodes we can actually it's 2, okay, because 0, 1, okay, 2, but 2 nodes. How many nodes?
How much nodes can you
travel from? Okay, yeah.
You just said travel.
Okay, how many nodes if we travel from node 0? If we can't visit any of the nodes in the forbidden set. Okay, so when we talk about graph problems, how many algorithms we can do? How many ways we can traverse the graph? DepthFirstSearch, yes.
DepthFirstSearch.
And?
DepthFirstSearch.
Yes, DepthFirstSearch. These are the two most classic way of traveling the graph. Remember the tree, we talk about the binary tree all the time, and trees are graphs, by itself, okay? Trees are a very special type of graphs. So we can use DepthFirstSearch, and we can also use the union find, disjoint set. Right? We'll talk about that later, in the next lesson. So these are 3 ways we can solve, 3 algorithms we can use to solve this problem. Okay, union find. Why? Union find is an algorithm we perform on a disjoint set. So basically, because this is a direction graph. So if there's an edge between 0 and 1, we can unite, we can merge these 2 nodes into a same group, right? So we can just perform these operations, and then later we can find out how many nodes in the group with this node 0, right? Simple as that. So today we talk about the DepthFirstSearch, okay? Simple as that. DepthFirstSearch, can you explain to me what's DepthFirstSearch?
Like, you start from the top.
Yeah?
You just go
Yeah.
and then
So basically, we follow a path,
You go
and
deep.
we go deep. We follow the path until we hit the wall. For example, like if it's a maze, right? It's a maze. If it's a maze, a maze, right? This is an entry, right? You want to find the exit here, right? So the DepthFirstSearch is just like you always walk, you always choose the left direction, for example, and then until you hit the wall, and then you try the other direction. So basically, you follow a path until you hit the you can't proceed any further, and you go back and change another direction. This is DepthFirstSearch. DepthFirstSearch, on the other hand, is that let's explore the area like close, okay, 1 meter, for example. And if you can't find the exit, okay, let's explore like 2 meters, or 3 meters, etc. Okay, yep, this is DepthFirstSearch. Okay, so let's implement the DepthFirstSearch. Should be very easy. Okay, define. Let's say we want to count f. We were given edges. Okay, for example, edges, and then we are given, what else do we need? And then the restricted, okay, this is restricted, let's say R. So we need to build a graph, right? We're given the edges. What the edges is from to, right? It's a list of the nodes from to, for example, like 0, 1 in this graph, 0, 2, 2, 3, 2, 4, 2, 5, and then 5, 7. We are given a list of the edges from and to, tuple, okay? So G equals default dictionary. Let's say default dictionary. And then for each one, we are building the graph using the adjacent list. So adjacent list, okay? There are two ways of representing the graph. One is adjacent list, the other is adjacent metric, right? Remember we talked about that. Adjacent list. Then for A, B in edges, so we have edges from A to B, then we have to say GA dot append. GA is a list, append B. And also, because it's undirected and GB dot append A, right? We have edge from A to B, and we also have an edge from B to A, okay? Okay, then we can perform this DepthFirstSearch, define DepthFirstSearch. So current node is I. So if I in the restriction list, or if I in scene. So this scene, we have seen it, right? So we have to define a scene hash set here. If we have seen it, if we have visited it, then we return 0. So there is no more nodes we can go. Otherwise, we say answer equal 1. For n e in gi, right? gi is the list of nodes that the vertex I points to. Then answer plus equal DepthFirstSearch n. Okay, so in here we have to put it in a hash set. Scene dot add I and then return answer. And the answer is obviously return. We want to return the nodes that we can visit from node 0, including the node 0. So DepthFirstSearch here. Okay. So here, let me explain. Okay. So here DepthFirstSearch. This is recursion, right? DepthFirstSearch calling itself. The scene table, the scene hash set. We need to remember the why do we need a scene hash set to remember the nodes we have visited? Right? Simple. We're visiting the 0. What's the neighbor? 1 and 2. Let's say we visit 1, okay? We DepthFirstSearch, we go as deep as we want, okay? But 1 also connects to 0. Then, if we don't mark the node 0 as visited, what happens?
Nothing.
Now we can go back and then we just, going back and forwards, okay? And then we'll be stuck here forever, right? So we have to use the hash set to remember the nodes we have seen, okay? And then this GI is basically the list of nodes that the vertex I connects to. So basically, we want to find out the vertex I, how many nodes it connects to. For example, here. Okay, if it connects to 1, 2, 3, then GI will be a list of 1, 2, 3. This is adjacent metric, right? We talk about adjacent metric. We're building the graph here, okay, and then we perform a DepthFirstSearch using the recursive way and return answer. The DepthFirstSearch function returns the number of nodes that this node I connects to, and we check if the node is in the forbidden set, then we return 0. Okay? Yes? Does it make sense here? Eric, does it make sense?
Ew, Pyro, you please smell disgusting.
Yeah, Eric, does it make sense? The term complexity. Actually O-V plus E, okay? Sometimes we say O-N, where N is the number of the vertex. But to be precise, we can say the term complexity is O-V plus E, where V is the vertex, E is the edges. The number of vertex plus the number of edges. The space complexity, we are using a hash set. So this is O-N, okay? And then recursion. These can go up to the depth n because we're following the DepthFirstSearch, and n is the number of the vertex. Okay, make sense? So we're using the DepthFirstSearch. So next lesson we talk about the BufferSearch. It could be
Okay.
similar. And another lesson we talk about union find. Okay, that's it for today. Bye bye.
Bye.
Bye bye.